Hello everyone and welcome to another lecture of EE316 Communication Systems. Today's topic is going to be on modulation techniques. In order for a signal that contains information to be transmitted through a communication channel, this signal must be changed, or in other words, modulated so that it is compatible with the channel. Modulation involves two signals. One of them is a low frequency signal, which is the message signal, and the other one is a high frequency known as the carrier signal. There are some well-known modulation techniques such as amplitude modulation, AM, frequency modulation, and phase modulation. Today's focus will be on amplitude modulation. AM is used for audio broadcasting on long, medium, and short wave bands. In military communication, AM is quite common since the message signal needs to travel for long distance. AM is considered as the simplest technique of modulations, as it is based on changing the amplitude of the modulated signal. It has got some advantages such as simplest to implement and can be demodulated easily by using demodulation circuits consisting of cheap components. But on the other hand, it has some disadvantages as well. It is not efficient in terms of using power, requires a lot of bandwidth, and sensitive to high level of noise. This is the AM process. We have a message signal, for example, in this type. After it is modulated, it is going to look something similar to this. This is the formula for AM modulation, and this is the carrier. We can see that the formula consists of the amplitude of the carrier 1 plus modulation index multiplied by the message signal, and then the rest of the carrier signal. So one important parameter here is the modulation index. What is modulation index? Modulation index is the ratio of modulating signal voltage to the carrier voltage, and it can be defined as Vmax minus Vminimum divided by Vmax plus Vminimum. If the modulation index is higher than 1, then it is called as or known as over modulation. If it is less than 1, it is under modulation, and if it is equal to 1, then it is 100% modulation. What does this mean? Let's say, for example, we have a message wave of 1, amplitude of 1, and a carrier of 1. So when we are using 100% modulation, this means that the amplitude of the modulated signal is going to be 2, which is the summation of amplitude of the carrier plus the summation of amplitude of the message. Again, if we have a message signal of 1 and a carrier signal of amplitude 1, then if we are using 100% modulation, the amplitude of the modulated signal is going to be 2, which is AC plus AM, which is amplitude of the carrier plus amplitude of the message. If we are using 50% modulation, which is under modulation, then the amplitude is going to be less than 2, which is 1.5. And if we are using 150% modulation, which is over modulation, then it is going to be 2.5. This is the block diagram of AM. As we can see here that the message signal x of t is multiplied by the modulation index, and then all of it is going to be multiplied with the carrier frequency signal, and the carrier signal is going to be summed with this product, and then we have the modulated signal as an output. To illustrate this, let's take a look at this example. Let's say that we have a carrier signal of 2 cosine 2 by 10 to the power 6t, where our carrier frequency is 10 to the power 6 Hertz, which is 1 mega, and we have a message signal of rectangle shape, and the modulation index is 1 over 2. So our result modulated signal is going to be 2, which is the amplitude of the carrier signal 1 plus modulation index multiplied by the message signal and multiplied by the rest of the carrier signal, which is cosine 2 by 10 to the power 6t. We can see here that the amplitude of this modulated signal is going to be 2 plus 2 over 2, which is 1. So 2 plus 2 gives us 3, we can see here that the amplitude of the modulated signal is 3. This is how we found it. 2 plus 1 gives you 3. Also, this graph is for the carrier frequency of 1 megahertz, and if we take the carrier frequency as 1 hertz, it is going to be something similar to this. Now we are going to implement all of this in the Simulink environment using MATLAB. So the block diagram of AM is in this shape, as we have mentioned before. We are going to construct and build this diagram and on the MATLAB Simulink environment. So we will start with constructing the message signal multiplied to the modulation index. Modulation index can be defined as the amplitude of the message signal divided by the amplitude of the carrier. So in here, let's define a modulation index of constant type, and it is going to have a value of 0.5, which means that our message amplitude is going to be 1 and our carrier amplitude is going to be 2. So this is our constant term. This constant term is going to be multiplied with the message signal. Let's choose a message signal of type sinusoidal. So sine wave. This is going to be my message signal, and it will have an amplitude of 1 as we have mentioned, and let's choose a frequency of 10. This 10 represents the frequency of the message signal. Since here it is defined as radians over second, this means that we are defining omega, so the term 2 pi is included in our frequency chart. Here let's choose a sampling time of 5 millisecond. Now let's make it even bigger, smaller. Now this is our message signal. Both of them, the constant and the message signal, are going to be multiplied with each other, so we will write product. Now it's time to define our carrier signal. Our carrier signal is going to be a cosine wave. So from the sine wave diagram, we're going to change this sine wave to become a cosine. How can we do that? By adding the phase term of p over 2. So by adding b over 2 in the phase, this means that our sine became a cosine signal. Our amplitude is going to be 2, and our carrier frequency is going to be something higher than the message frequency, anything higher than 10. Let's choose, for example, 100. So 2 by 100, same logic, this is omega, so that's why the term 2 by is included, and our carrier frequency is 100. Sampling time should be the same, so 0.0005, and let's press OK. After that, the carrier frequency and the product of the message signal with the constant is going to be multiplied. So product term is added and the links are connected to it. After that, we're going to sum this product with the carrier signal. So we're going to define the sum block here, and this sum block is going to be attached to the product of all of this and the carrier signal itself. This represents this part of the block diagram. Our output is going to be the modulated signal. We're going to see it in the time domain by using the scope, and in the frequency domain by using the spectrum analyzer. So this is our scope, and this is our spectrum analyzer. Let's run it and see the result. So this is our modulated signal in the frequency domain. We can see here that 0.1 kilohertz, which represents the carrier frequency, is the center of the spectrum, both in the right side and on the left side. Also, let's focus here. We can see that here, this side, this is the right side part of the modulated signal. The upper side is 0.11 kilohertz, which means 110 hertz, which is the summation of the message frequency plus the carrier frequency. We have a message frequency of 10 hertz and a carrier frequency of 100 hertz. So the result here is going to be 0.11 kilo, which is 110. This is how it is represented in the frequency domain. Let's take a look at the representation in the time domain. In the time domain, this is our modulated signal. This is the shape of it, and it has an amplitude as expected of 3. We have spoken about this in the previous slides. So it is as expected, an amplitude of 3 is observed. Instead of doing the block diagram by ourselves like in this way, there is an easier way by using this Simulink environment. There is, let's delete this part first. There is a built-in AM modulation block, which is called DSB AM modulator passband. DSB AM modulator passband is equivalent to the block diagram that was built previously, and which is equivalent to this block diagram right here. So all we have to do is introduce a message signal of sine wave, for example. Same message signal, not this type, but sine wave. This is going to be our message signal. Here, same thing, amplitude of 1, frequency of omega of 2 pi, and the frequency is 10, and the sampling time is 0.0005. In here you don't have to include the term of modulation index, because it is going to be calculated automatically using the DSB AM modulator passband. So just the connections. And from the DSB AM modulator passband, we're going to choose the input signal offset, which means the amplitude of the carrier, which is 2, and our carrier frequency was 100. So this is equivalent to the block diagram of AM. Let's take a look at the results. Same results as we can see here. This is 0.1 kilohertz again, which is 100 hertz. This is our carrier frequency, and in here this is 0.11, which is 110 hertz, which is equivalent to the summation of the carrier frequency with the message signal. In the time domain, amplitude is still 3, and this is the shape of the modulated signal. Now in here this is the carrier, and sometimes there is no need to represent the carrier, and this type of modulation is called or known as DSB AM DSB suppressed carrier. This is the block diagram of the DSB suppressed carrier. We're going to implement this using the MATLAB environment and see the result obtained. So first, we're going to start with doing the message signal multiplied by half and minus half multiplied by the message signal. So we need the message signal of type sine wave again. It is going to have the amplitude, let's say this time is going to be 2, because we are going to multiply it by half, and the frequency again 2 by 10, with the sampling time similar to the previous one, which is 0.0005. So this is our sine wave, which represents the message signal. This message signal is going to be multiplied by 1/2. So we're going to introduce the constant term again, and it will have a value of 0.5. These two terms are going to be multiplied together, so product and also it is going to be multiplied, as we did in the previous example, with the modulation index. So modulation index is a constant type, constant, and again that has a value of 0.5, as mentioned in the previous example, since the amplitude of the message signal is 1 and the amplitude of the carrier frequency is 2. These two terms are going to be multiplied together, so we're going to introduce a product now. To transfer all of this to just one simple block diagram, so that our shape will be, we will save some space here for working, we're going to highlight all of this. We're going to highlight it, right click, and then we're going to create subsystem from selection. Create subsystem from selection will give me this result. So this is like a subsystem. When we double click on it, it will take us to the thing we have implemented. How to get back? Easily, just click on this arrow and we are back to our workspace. We're gonna do exactly the same thing but with minus half. So let's just try to copy this. We paste it here, and instead of this 0.5, it's going to be minus 0.5. You can do the copy and paste command easily on the Simulink environment. So again, highlight it, right click on it, and create subsystem from selection. We can delete this output. So this is my one half of the message signal, and this is the minus half of the message signal. Now what is left? This part is left, which is the AM modulation. How did we do AM modulation in the previous example? The message signal, which is in this output subsystems, is going to be multiplied with the carrier frequency. What is the carrier frequency? Again, a sine wave, which is shifted by phi over 2, p over 2, which changed the sine wave to become a cosine wave. Our amplitude is 2. Our carrier frequency is 100. And the sampling time is 0.0005. So what will happen with this carrier signal? Let's name it carrier. It is going to be multiplied with both message signals. So we have two product boxes. One is connected to each carrier signal and each message signal. Now after that, the summation, as we can see here, the summation of these two resulted products is going to be implemented. So we will add a sum block, 3 sum block, one here and one here, and this a summation here and a subtraction in here. So another sum and the last one here. Now in here, this part, this is important. Instead of this pipe being here, we're gonna transform it and we're gonna change it and make it to the left. This will change the shape of the arrows. This arrow became downward. In here also, instead of the beginning, we're gonna take it and then it will be in the middle, and this is going to be subtraction. As we can see here, this is subtraction. So we're gonna just connect the links, this to here, this is to the cosine carrier, also to the cosine carrier, to the product, to the summation, to the summation. This diagram, this block diagram is now equivalent to the block diagram of this AM DSB suppressed carrier. Now it's going to be connected to a scope as usual and a spectrum analyzer. So this is our spectrum analyzer, this is our scope. After that, let's simulate it and observe the results. So here from the spectrum analyzer, we can see that the suppressed carrier means that the carrier is not represented anymore in the frequency domain representation. Here, there was a carrier here, spectrum at 0.1. Now it does not exist anymore, and this is still at 110 Hertz, the summation of the message frequency with the carrier frequency. As in the AM modulation, instead of doing all the block, there was a DSB AM modulation block. This is similar to AM modulation of type suppressed carrier. So instead of doing all of this, we can just easily leave. Let's delete all of this. It's called DSB suppressed carrier AM modulator passband. So DSB suppressed carrier AM modulator passband is going to be connected to the message signal, which is sine wave. Same thing, amplitude of 1 and the frequency of 2p100 and the sampling time of 0.0005, and also the DSBM. This is the carrier frequency we have chosen to be 100. This is not 100, the message frequency was 10. Now we're gonna connect the scope and the spectrum analyzer. We should obtain the same results compared with the block diagram that we have implemented in the previous example. Let's run it and let's see. As we can see here, same again, the carrier is suppressed. There is no more frequency spectrum in the 0.1 kilohertz, and this is still at the 0.11, which is 110 hertz, which is the frequency of the message plus the carrier frequency. So this brings us to the end of this lecture. I hope that it is understandable. I wish you good luck and see you in the next lectures. Thank you for your listening.